we're going to look at projectile motion, but this time not a horizontal launch, but a launch that's from the ground to the ground. Imagine we have the ground here. So we have a person kicking a ball. The initial velocity is up and to the right. And as the ball moves through the air, the velocity's direction changes slightly. It becomes smaller until it stops moving in the y direction and it's only moving in the x direction. Once it reaches the highest point, it'll start coming back down and have a velocity down and to the right. Once it reaches back to where the same height it started from, the velocity will be equal in magnitude, that means the same length, but just opposite in direction. So initially, the ball was kicked at an angle above the horizontal, and then when it comes back down, it'll be moving at the same angle but below the horizontal. Now the velocity does stop moving in the y direction at the highest point, but notice that the object continues to move. So the velocity in the x direction is not 0. So the velocity in the x direction is not 0. Now just like for horizontal projectile motion, we had to look at what was happening in the x direction separate from what's happening in the y direction. In this case, we have to do the same thing. But instead of the object only moving in the x direction initially, it's moving in the x and y direction initially. So let's look at that. So initially, the velocity was up and to the right, above the horizontal. And you can almost think of it as being the hypotenuse of a triangle, where this is the x-axis and this is the y-axis. Now, the x and y's can be thought of as being part of this triangle where there's an angle, and I'm going to use the symbol theta for the angle. And so if I think about trig, the cosine of an angle is the adjacent side, which in this case would be x, over the hypotenuse, which in this case would be the velocity. Now I want to be a little more specific. This is not just any old x, but it would be the velocity in the x direction. So velocity in the x direction over the overall initial velocity. Now if I multiply both sides by v, the initial velocity, then my velocities will cancel over here, and I'll be left with that the velocity in the x direction is equal to v times cosine of theta. That is how we find the component or the piece of the velocity that's in the x direction. Now for the y direction, or the up and down direction over here, again, this is not just y, but it's the velocity in the y direction. And it's opposite of the angle. So if this is our angle, this side is opposite, and opposite over hypotenuse is sine, the sine function. So the sine of theta will be this velocity in the y direction over the initial velocity. I'm going to do the same thing where I multiply by the initial velocity on both sides, and then that will give us that the velocity in the y direction is equal to v times sine theta. And so that's how we're going to separate our initial velocity into its components. Now similarly, if I had the final velocity here, I could separate it into an x and a y component using the same relationship. Just like we did for finding the final velocity of an object right before it hits the ground when we had projectile motion with a horizontal launch only, we can also think of the velocity, this overall velocity, as being part of the velocity in the x direction squared plus the velocity in the y direction squared. We can think of it, this is called a resultant. It's the result of having the x and the y together. Now, if I'm looking for this angle here, and I have an opposite and an adjacent side, just like we did before, you can look at the tangent function as being opposite over adjacent. Opposite in this case would be the velocity in the y direction over the velocity in the x direction. And then to solve for the angle, we would need to take the inverse tangent of both sides.